In this video, we learned the third of the four big theorems that we're learning this semester, and that's Stokes' theorem. Let me give you the statement of Stokes' theorem, and then there's a clarification or two that I need to make here. So the setup is, let S be an orientable surface with boundary C. So you might imagine a surface in space, and C is its boundary curve. And the surface and the boundary have to be oriented compatibly, which is the thing I'll clarify in a couple minutes. Let's say that F is a vector field on the surface S. Then Stokes' theorem says that the integral along C of F dotted with ds is equal to the double integral over S of the curl of F ds. Now you'll notice that I've left this a little bit incomplete, because I want you to use your context clues to figure out which ds is going to go in each place. Think about it for a second. Notice over here, I'm integrating along a curve, which means that this is going to be a little ds. And in order to carry out a dot product, this had better be little vector ds. That's the only thing that would make sense in this context. Now let's look at the other side. When you take the curl of a vector field, that gives you another vector field. So there has to be a dot here in order for the right-hand side to make sense. Also, since I'm integrating over a surface, doing a double integral, this has to be a big ds. And last of all, if I need to carry out a dot product here, I need to dot a vector with a vector. So this one needs to be big vector ds. So putting it together, Stokes' theorem says that the integral over the boundary curve of f dotted with little vector ds is equal to the integral over the surface of the curl of the vector field dotted with big vector ds. Now let me tell you what I mean by having the curve and the surface oriented compatibly. Remember that when we have an orientable surface, that means that it's possible to assign a unit normal vector to each point in the surface. And there are two choices for that. And the orientation has to be given in the problem. So let's say that we've given the surface the orientation indicated by that vector. Then in order for the boundary to be oriented compatibly with that, we need to orient the boundary curve counterclockwise around that normal vector. So along this edge, it would mean going in this direction. Now, if the surface had been given the opposite orientation, a downward orientation in this case, then C would have had exactly the opposite orientation. So what you notice here is that the boundary curve is going counterclockwise around the normal vector, and that might help you see how Stokes' theorem is actually a generalization of Green's theorem, where we had to orient the region and the boundary curve in the same way. Now, something else that can happen is that your surface may have more than one boundary component. So, for example, your surface might look like a hemisphere maybe with a hole cut in it. And let's say that we give this hemisphere this orientation. Then I need to orient the boundary curve compatibly with this orientation. So, looking down here, I would need to go counterclockwise around that. And notice that that would be from right to left from the way that we're viewing it. So this bottom boundary would be going in this direction, counterclockwise viewed from above. Whereas up here, if I want to go counterclockwise around this normal vector, notice that that would give it an orientation that appears clockwise from our perspective. Now there's another way to characterize the way that you orient the boundary curves that might be a little bit more intuitive to you. Let's say that you are standing on this edge and your head is pointing in the direction of the normal vector. Then you want to walk around the boundary so that the region stays on your left side. And notice that if you're walking this way, then the region S is over here on your left. Similarly, if I'm standing on this boundary curve, or maybe I'll mark it here, and your head is pointing in this direction, in the same direction as that normal vector, then the region is on your left side. Whereas if you're standing at a point here, and you want to orient that region so that the boundary stays on your left, you're actually going to have to walk around in this direction, because your head would be pointing out this way, and the surface would be over on your left side. So either of those two ways you can think about the way to orient the boundary and the curve. Now, one thing that students sometimes find confusing is they'll look at a picture like this and think this top part is also a boundary curve. Let me see if I can kind of explain why it's not. If I draw an entire sphere, that entire sphere has no boundary. But if I cut it, so think about this as a tennis ball. If I cut this tennis ball in half, then I'm going to have a raw edge along the bottom here. So this curve that I'm drawing in purple would be that cut edge. It's the cut edge that counts as a boundary. This is just what you see when you look at the surface in perspective. This is not a raw edge of the surface. It's just what you're looking at in profile.